Beyond the heliosphere, our home in the galaxy that protects us from deadly cosmic radiation, lies the vast emptiness of space. Empty? Not quite. In fact, across the Milky Way, the enormous distances from star to star are all filled with matter. But what is it, and from where did it come? New samplings by NASA's IBEX spacecraft, the Interstellar Boundary Explorer, reveal more about the nature of this matter that is the basis for stars, planets, and even us humans.
Good afternoon. My name is Dwayne Brown with the Office of Communications, and welcome to NASA headquarters. Today, you will hear and learn about the anatomy of our galactic neighborhood. The information is available on the web at www.nasa.gov/IBEX, and also via Twitter, Facebook, YouTube, and other social media sites. We'll have brief presentations from our presenters, then open it up for questions starting here in Washington and go to our phone lines. We have a lot to cover. Let's get started. And let me first introduce you to today's speakers. First up, Dave McComas, IBEX, Principal Investigator and Assistant Vice President of the Space Science and Engineering Division at Southwest Research Institute in San Antonio. Priscilla Frisch, Senior Scientist, Department of Astronomy and Astrophysics at the University of Chicago. Eberhard Mobius, Professor, Space Science Center and Department of Physics, University of New Hampshire, and who's currently visiting professor at the Space Science and Applications Group, Los Alamos National Laboratory in New Mexico. And Seth Redfield, Assistant Professor, Astronomy Department, Wesleyan University in Middletown, Connecticut. So with that, I'll toss it to Dave.
Well, thank you very much, Dwayne. We are incredibly excited to be here today to tell you about some first observations of interstellar material, really alien matter, stuff that didn't come from our sun, didn't come from our solar system, our Earth, but came from the outside, from other parts of the galaxy. And we're making these first measurements with the IBEX Interstellar Boundary Explorer mission. And this material, this alien interstellar material, is really the stuff that stars and planets and people and all of us are made of. So it's very important to be measuring it directly, a number of these species for the first time. All these results are coming out today in a set of 6 papers in a supplement to the Astrophysical Journal, Time to go with this press conference. And before we get into that, I think we need to give you a little bit of background. So let me start with the heliosphere. If we can go to the first graphic, you'll see our heliosphere, just a schematic diagram of our heliosphere. The solar wind is a 1,000,000-mile-an-hour wind that blows out from the sun all directions in space all the time. And it basically inflates a bubble in the local part of the galaxy. And that bubble we call the heliosphere. Now, heliosphere is nothing more than the Greek word for sun, helios, and the region of influence, sphere, or region of influence. So the heliosphere is the region of influence of our sun. And it plays a very important role because it protects us. It protects the inner solar system from dangerous galactic cosmic rays, the majority of which would come straight into the planets and the inner part of the solar system if it weren't for this structure out there about 100 times further away than the sun is from the Earth, the heliospheric boundaries. And so it's a very important region for us as humans, and it's especially important region for us as spacefaring people, because when you get away from the Earth and the protection of the Earth's atmosphere, these cosmic rays are even more important and more dangerous. So moving on to the next movie, what you'll see here is the IBEX spacecraft. It was launched in 2008, October of 2008. It's only about 3 feet across, 1.5 feet high, and it weighs about 200 pounds. So it's a very small spacecraft. It points at the sun, and the blue panels that you see on the front are solar panels, just like you have on the roof of some houses. That's where we get our power from. And we look out the two sides with these very, very sensitive cameras, which are able to detect neutral particles coming in from the far edge of the solar system. And so that's IBEX. It's part of the Explorer program here in the Heliophysics division. And Explorer is the longest running and, frankly, the least expensive sort of missions that NASA does. So it's a tremendous amount of science we're getting out of this very small spacecraft. So if we can go to my next movie, you'll sort of get an idea of what it looks like from the outside of the galaxy. This is obviously an artist's rendition. But as we zoom in, you'll see us coming in past the billions of stars that make up our galaxy, spiral arms spread around. And we're about halfway out in one of the spiral arms. As we go, and you can see our heliosphere as it moves past the interstellar wind. Now look at this little region here, and let's ride along with the particles that are headed right towards the nose of the heliosphere. The light blue ones are charged, and we get to the heliopause, that boundary, it pushes away those particles, and they're lost. But the neutral particles aren't affected by the magnetic fields, and they can come directly into the heliosphere. Some of them fly in past the planets and the moon towards the Earth, and a very few can come directly into the aperture of the IBEX spacecraft and be detected. That's after about 30 years and traveling 15 billion miles, and I like to call it the 15 billion mile hole-in-one. And with that, I think we'll move on, and Priscilla will tell you about the local part of our galaxy. Priscilla?
Oh, thank you very much, Dave. I'm going to talk about interstellar clouds. Interstellar clouds are clouds of material between stars. And the IBEX is sampling a very low-density, tenuous interstellar cloud. So it's very different from the clouds that we see in Orion or something like that. Start the animation, please. We're going to start our journey into the galactic neighborhood from our Milky Way galaxy. And as we zoom in, we'll see spiral arms that are full of giant, dense clouds, massive stars, and dust. And next slide, please. Orion Nebula is a beautiful example of a very dense dust cloud. It's nothing like we have around the sun, but in a cloud like this, stars are born and they die as supernova and make the elements that we are sampling. In the right of the nebula, you'll see these beautiful arcs and bubbles that actually have been blown by the stellar winds from brand new stars inside the Orion Nebula. Next slide, please. This is the remnant, the debris of a supernova explosion that happened 1,000 years ago and was observed by our ancestors. It was called the Crab supernova explosion. And when the Crab exploded, it cast many of the elements that IBEX observes into space. The periodic table shows you the hydrogen, helium, oxygen, and neon that IBEX is observing right now, the first direct measurements of interstellar material made without a telescope. The animation, please. Now we're going to leave the dense clouds behind us and journey into the very tenuous, sort of fluffy interstellar clouds that surround the sun right now. We're actually in a complex of clouds, and they have names. Seth has named some of them. You see, we are right at the edge of what we call the local cloud. That's the bright yellow dot in the center of the figure. And you can see that we're actually moving with respect to these clouds. The yellow arrow shows the direction of the sun's motion. Now, because of this motion, interstellar gas and dust are blown through the heliosphere at this incredible velocity of 50,000 miles per hour. And this, both dust and gas are blown through the heliosphere, but IBEX is only measuring the gas component, of course. And you see that we're at the edge of the cloud. One of the reasons that we know that we're at the edge of the cloud is the next cloud over is in front of the galactic center. It's called the G cloud, and you see that the star Alpha Centauri is right behind the G cloud. When we look at Alpha Centauri, we do not see the local cloud, and that tells us that we have to be at the edge of the local cloud. Please start the animation. And the blue arrows show you the motion of these clouds. Because of the relative sun-cloud motions, we change clouds every 45,000 years. We've actually only been in the local cloud for about 45,000 years, and all of the data indicates we're going to leave it in the next few thousand years. And when we leave it, Eberhard, in his instrument on IBEX, will be measuring something different, but we don't know what. So, Eberhard.
Thank you, Pris, for sending by these clouds. And if we are in our solar system, we see the effect, the wind blowing right through our solar system. But let me remind you, the solar wind inflates this bubble, the heliosphere, which keeps out the charged component, and with that, the dangerous cosmic rays. But the neutrals, they punch right through it, and they make it all the way to the Earth. And here, IBEX catches this wind, and I must say personally, that's what excites me the most. That's the part of IBEX that I was looking forward to when we started IBEX. Now, to view this, let's take the next slide, and we board the Enterprise now, which brings us far away from the sun, and now Geordie LaForge lends us his visor, and when we look up, we see the interstellar wind as a bright spotlight beckoning at us from Scorpio. You see Sagittarius to the left and Libra to the right in a view that you can see around midnight in June when looking south. Now let's animate that and rush back to the Earth, and the view opens up to the entire sky. And at Earth, our IBEX visor awaits these particles, and you see it transitioning to an IBEX map where the bright red wind comes now from Libra. Well, why has it shifted from Scorpio to Libra? The culprit is the sun. With its gravitational field, it bends the flow around, like if you shoot up a soccer ball straight into the air, it is forced to fall back to the ground in a curve. And in the next view, we view that from a vantage point high up above the North Pole, looking down. You see the flow trajectories as they are bent by the sun's gravity. Now, IBEX, a sun-pointed spinner, can only view these when the flow comes right along the Earth's orbit, and that happens in early February, actually coming up in a week or so, and we are excited to see this one more time this year and how it has changed. Now, the flow trajectories, depending on the speed, are different. The darker blue is a slower flow that gets bent more than the lighter blue, which is faster and shoots by. Now, IBEX sees the slower stuff earlier in the orbit than the faster stuff. This is our speedometer with which we can actually nail down how the interstellar wind, how fast it is, and then relating it to astronomical observations, we can tell which one of the clouds we actually call home. So the next view shows the results, the speed up and the direction in longitude to the side. And our new results taken with the two different ways of using this speedometer shows us where we are. Compared to the old result, it's a little bit slower and a different direction. That's what you see in blue. But this solves a puzzle. The old result really didn't put us into any of the neighboring clouds, but with the new result, we are right in the local cloud. Isn't Mother Nature amazing? It provided us with a speedometer just for free. And this new result has some interesting consequences. Also, the pressure on the nose of the heliosphere is less than we thought before. Now, Seth will take this up a little bit later, but before we go there, let's turn to another capability of IBEX, namely to also sort out the elements of this flow. And IBEX has seen hydrogen, oxygen, and neon for the first time in addition to helium, which we've seen before. And a key result is that the local cloud actually is somewhat different in composition than the sun and the Milky Way as a whole. There's less oxygen compared to neon in our neighborhood than in the sun and the Milky Way. That leaves us with a puzzle for now. Could it be that some of that oxygen, which is so crucial for life on Earth, is locked up in the cosmic dust? Or does it tell us how different actually our neighborhood is compared to the sun's birthplace? Only time, some more data from IBEX, and hard, but I can tell you really exciting work will tell us. Seth, what's your take on this?
Thank you, Eberhard. Well, my job is to provide a little perspective from someone outside of the IBEX team and to talk a little bit about the broader implications of these results. And let me begin by saying how exciting it is that we know where the sun is located now relative to these interstellar clouds. So much of what we do when we explore the cosmos is try and put ourselves into some sort of context. Ourselves, the Earth, the sun, and IBEX has done that with these new discovery. With my first slide, I show two images that you've seen before. On the left is the view that Priscilla showed, and it's a view of this collection of interstellar clouds right around the sun, and they're all moving with their own unique motions. And the two nearest clouds, the local cloud and the G cloud, we've known for some time that there is a discrepancy between the motions that we observed for these clouds by looking at nearby stars and the old results of atoms streaming into the solar system. There's a discrepancy there that we couldn't quite explain. Now these new IBEX measurements match the motions that we observed with stars for the local cloud perfectly. And what this does is it pinpoints our location inside the local cloud. We're very near the edge, but now we know that we're in the local cloud. And location is really important because the heliosphere is essentially the balance between the outward moving solar wind and the compression from the gas and dust that surround it. So if you're in a different interstellar medium environment, you're going to create a different heliospheric structure. And so the heliosphere changes with time. As it passes into a dense interstellar cloud, it'll be compressed and very small. And as it moves into another cloud, it'll expand out again. And this has consequences, again, for shielding us from these dangerous galactic cosmic rays. So learning about the heliosphere today actually helps us understand the heliosphere as it was in the past and how it will be in the future. Because now we know where we are, we know where we're coming from, and we know where we're going. These results also go well beyond just the sun and the heliosphere. And because the phenomenon of an outward moving stellar wind and a compression from surrounding gas and dust is so common that we think most, if not all, stars have a structure that's analogous to the heliosphere. And those we call astrospheres. And in my next slide, I actually show several examples of these astrospheres. And these are very dramatic examples of stars moving through a dense interstellar medium or stars with very, very strong solar winds. And the image on the bottom is particularly striking. It kind of looks like a comet. But what's happening is the star is moving so quickly that you can see the wake of its astrosphere being spread out in its path. It's kind of like the jet trail from a jumbo jet flying overhead. And because of the great diversity of stars and the incredible diversity of different interstellar medium environments, the number of configurations that you can have is endless. So we're going to be presented with this vast zoo of astrospheres. And the gold standard with which we're going to study these astrospheres is going to be our heliosphere. And so we really need to have a wonderful three-dimensional, detailed understanding of our own heliosphere with which to evaluate these other structures. And then finally, on my last slide, I wanted to talk a little bit about the implications of these discoveries in the future. And I zoom in again into our very local cosmic neighborhood. You can see the local cloud and the G cloud there. I've indicated the locations of known detected astrospheres. So unlike the really dramatic examples I showed in the previous slide, finding astrospheres around stars like the sun is a little bit difficult. And it's only been in the last 10, 15 years that we've actually been able to refine the techniques and find the instrumentation with which to make these discoveries. And so in this very local volume, where there are about 100 stars, we know of about 10 that have astrospheres. Alpha Centauri, the nearest star system, has an astrosphere around it. We're also discovering exoplanets. And I've also indicated the location of stars that have had planets discovered around them. And we know of at least 2 cases where we've discovered both a planetary system and an astrosphere around it. And these are the true analogs to our own solar system, where we have a heliosphere that protects us from galactic cosmic rays, us here on Earth and the other inner planets. Well, we have another example where that star with its own astrosphere is protecting the planetary system around that particular star. And in the next 10 years or so, I think we're going to be opening up new research areas, asking totally new questions that we couldn't have addressed 10 years ago, 15 years ago. And it's because all these things are coming together. We're finding planets, we're finding astrospheres, and we're making great strides in understanding the heliosphere that surrounds the sun. And so I think we'll be addressing how this shielding of dangerous cosmic rays impacts things that happen on planets, and in particular, could affect the habitability of these planets. So with that, I think I'll pass it back to Dave, who had some summary remarks.
Yep, thank you very much, Seth. So today we're announcing these first observations of, direct observations of interstellar material, hydrogen, oxygen, neon, quantitative measurements of those to join previous measurements that had been made before of helium. These are really important elements to know quantitatively. These are the building blocks of stars and planets and people. So it's very, very important to know about them. We've discovered this big puzzle that the matter just outside of our solar system doesn't look like the material inside from the sun and in the solar system or across the galaxy on average, as far as we know. And it seems to be deficient in oxygen compared to neon, which leaves us with this big question, this big puzzle. Is it really such a different region that we happen to be in right now, unrepresentative in some way, very different from where the sun was formed? Or is that life-giving oxygen locked up in other things, locked up perhaps in dusts or ices that float around through the interstellar medium? And finally, we've caught this interstellar wind and we've measured its speed, and it's not as fast as we thought it was going. And that has a very important implication because the pressure it provides on the front of the heliosphere is less. And so the heliosphere is actually then more dominated by the external magnetic field and less by this flowing in material than we expected. That has important implications for what the heliosphere structure is like and for answering questions about how exactly the heliosphere does this critical shielding of cosmic radiation. And I guess I'd add, finally, on a personal note, I'm just delighted that we were able to do all this in one of the smallest and fastest and least expensive things that NASA does, a small explorer. And with that, Dwayne, we'd love to take some questions.
Will do. And excuse me, congratulations to the team. And Eberhard, I really enjoyed the Enterprise touch you put in there. I'm sure if Bach was here, he would say fascinating. So for the question and answer period, we are going to start here in Washington. And if you can wait for the mic and give your name and affiliation and pose your question.
Hi, my name is Abdul Aziz Khan, and I'm from Voice of America Television. And my question is for anyone who would like to give their insights into this. Of all the discoveries, if you were to point out one discovery which would have the most impact on science in the next 5 years, what would that be? Thank you.
Well, that's a great question, and I think we'll probably answer it with 2 or 3 different answers because we may feel individually that the different one is the most important one. Seth, what's your take on that?
Well, I think the discovery of other planets, coupled with our understanding of the impact that these galactic cosmic rays could potentially have on planets themselves, or even the emergence of life or the evolution of life, is really fascinating. And I'm really excited by these connections between things here in our world, on planet Earth, things that are happening with the flow of gas and dust streaming through our galaxy. I think there are actually connections there that we haven't explored fully. And now with these results from IBEX and these other discoveries, they're all coming together into a really interesting topic.
Well, yeah, I would like to add, I just recently read that there must be basically around every star in this galaxy, there must be planets. So there's new evidence for that. So if you put that together, there must be life out there, probably not looking like we, as in Star Trek, they always look alike, but there must be some intelligent life out there, and maybe someday we can communicate, although over this large distance it's a long drawn out discussion. And I think that's really profound to not have just this unicate of life on Earth. There are gazillions of species, but it's life as we know it here, and who knows what is all out there.
I guess I would have to say I'm not so sure that there is life out there. I don't know one way or the other, but I do know that these astrospheres will provide a very important part of the process, if there is life, for the formation of life, because they do provide this critical shielding. And that's the part that we've really been studying and that we're able to do quantitatively now with measurements from IBEX.
So,
Priscilla?
well, I actually think understanding our galactic environment, including the heliosphere and astrospheres, is probably the most exciting things that IBEX is doing. But I think the one that's going to have the widest implications scientifically is actually the neon to oxygen ratio, because the neon to oxygen ratio is directly telling us about one of the most mysterious elements in our neighborhood of the galaxy, which is oxygen. When we look at the stars, we don't see enough oxygen. And so we assume that that oxygen is on interstellar dust grains, but we can't observe it on interstellar dust grains. There are some grains that have water ices on them, but not very many. And so the mystery is, where is the oxygen? And the IBEX measurements are giving us the oxygen abundance in an interstellar cloud, where we probably, hopefully soon, will have the best set of information that we can have on any interstellar cloud. So I think as far as scientific implications, the neon to oxygen ratio, which is telling us about the interstellar dust, is going to affect a huge range of astronomy. There's so many astronomical questions that hinge on things like that, issues like that.
So there you go. That's our one best favorite part.
Eric?
Eric Hand with Nature. I guess my question is for Dave. So we have these two pieces of news. One, the helium, or sorry, the neon and oxygen ratios, but also it seems that you're saying that these results are affecting our picture of not only where we are in the local cloud, but also the shape of the heliosphere. And I was hoping you could put up that slide again, which has me perplexed, and explain what it is that you measured and how it's affecting our picture of where we are in the local cloud and what the change is,
Sure.
the new picture
Yeah.
of what the heliosphere looks like.
Yeah, great question, Eric. Thanks. So if we go back to that graphic, and I see that they have it up already. So this is the structure as we've tried to understand it over the last 5 or 10 years or so. And we know about the termination shock because the Voyager spacecraft had crossed the termination shock, and they're in the inner heliosheath beyond the termination shock and inside the heliopause, which is basically the boundary between the solar material on the inside, the galactic material on the outside. What we've learned is this interstellar medium that you see on the right flowing in is actually moving enough slower that pressure is about 20 to 25% less than we thought it was before. And one of the things we learned earlier from IBEX with the IBEX ribbon was the importance of the external magnetic field. And we thought, well, almost everything's driven by this flowing pressure. And then we learned with the earlier results from IBEX, no, it's that's important, but also important is this external magnetic field. Now what we're learning is the flow is even much less, maybe 25% less pressure, which makes the external magnetic field component even more important. And so my picture of the heliosphere now is that this is even more compressed by the external field, even less driven by the inflowing pressure. And I'm not even sure today that that bow shock that we've been drawing in for decades exists at all, given these flow
In my mind, inflowing material is also a compressing sort of thing.
Right.
Why are you saying that those are counterposed, that the external magnetic field is
They're-
compressing but with lesser inflow?
There are two different types of pressure. There's pressure from moving material. When you drive your car down the street, you push through air, and the faster you go, the more pressure it puts back on you. Okay, that's the pressure from the interstellar medium. There's also pressure from magnetic field lines, which are sort of like, think of bungee cords. Think of having pulling a beach ball through a room filled with bungee cords from floor to ceiling and having it squeeze that beach ball as you pull it through. Both of those types of pressure occur on the outside of the heliosphere. But what we've learned now is that flowing pressure from the interstellar medium is much less significant than we thought it was before. And that means that balance between the two is different. And that could have pretty significant implications for how the exterior structure of that interaction really works.
So what is the shape then?
Well, that's a good question because we don't exactly take a picture of the shape, but it's probably a lot more compressed along the field and not as blunt as we thought. The tail on the backside is probably offset, not exactly in the anti-flow direction, but pulled more down towards the direction of the external magnetic field and that sort of thing.
All right, we're going to now go to the phone lines. And first up will be Denise Chow from space.com. Denise?
Hi, thanks for taking my question. I think this is probably for Dave. I'm just wondering, as we're going into an increased phase of solar activity, how you think that will affect this region and the observations that IBEX will be able to make. Are you expecting to see more dynamic changes?
Yeah, that's a great question. Thank you. So as I said at the start of the heliosphere is actually inflated by this 1,000,000-mile-an-hour solar wind that flows out all directions in space all the time from the sun. And this balance that we're talking about that's creating the outer heliospheric interaction is a function both of what's coming in from the outside, which is what we've talked about today, and we have a lot of new information on we didn't have before today, and what's pushing out from the inside, which is the solar wind. And so the increasing dynamic pressure and the more variability in the solar wind will actually try to inflate the heliosphere a little more, at least temporarily. And the variability means that the whole heliosphere is likely to sort of breathe and vary as we head into solar maximum. And so it'll be somewhat of a different interaction. That's pretty interesting for us too. And something else that we didn't mention, but IBEX was moved into a very long-term stable orbit last summer, and is now in a position where we have consumables, hydrazine gas, and it's a low radiation environment where we hope that IBEX will actually last for another decade or more. So that we'll actually see a solar cycle's variation in the inflation pressure from the inside. Eberhard?
I would like to add to that the solar cycle has also a profound influence on this interstellar wind that comes in. It comes in neutral, but the sun with its ultraviolet radiation ionizes part of this wind, so robs the atoms of electrons, and then the solar wind sweeps the charged particles away. And that is different for the different elements. And since Priscilla mentioned that the ratio between oxygen and neon is a really key measurement, we can take that measurement more precise if we can really hone in on this loss on the way. And if you follow that over the solar cycle, it gives you a much more precise measurement tool to do that.
Okay, we're going to come back here. Any other questions from the audience? One last question from one of our museums on the network here, and this is for everyone. So get your thinking caps on here. It's sort of a visionary type of question. The importance individually that you all feel of studying this type of science, heliophysics, and what the science IBEX is doing. And as a human race, human society, why should we care? How's it going to affect us? And your personal opinions on that. Dave, we'll start with you.
Sure, I'd be happy to start with that. Heliophysics is a really incredibly interesting and important field. It ties together what's happening on the sun with the space that surrounds our Earth and affects our Earth and technology and life on Earth, and extends all the way out to these outer boundaries of the heliosphere, hundreds of times further away from the sun. And so it tells us things about the part of space that we live in and the interaction of that part of space with the rest of the galaxy. But it also tells us useful and helpful things, because these interactions can have an effect on our technological systems. Large space storms, for example, have an effect on our GPS and on other satellites. The galactic cosmic rays coming in from the outside have an effect on astronauts' ability to go on long-duration space missions and hopefully go to Mars and beyond in the long run. And so it's a very interesting field of really core fundamental science that also affects us personally. And it's for me, it's an incredibly exciting field. So that's my take. Priscilla?
Oh, well, it's all very exciting. But I think one of the most interesting possible implications is that as the sun moves through space and moves in and out of interstellar clouds, the flux of galactic cosmic rays at the Earth really changes. And that's recorded in the radioisotope record that geoscientists are measuring. And someday, maybe we'll be able to link the sun's motion through interstellar clouds with the geological record that is tracing the geological history of our Earth. I think that would be really exciting if we can ever do that.
Robert?
Well, I find it really exciting that right at our front doorstep, we can take a sample of this interstellar matter around us. And if you think back all the way to the Big Bang, there was only hydrogen and helium, and then stars and supernova sprinkle this with the heavy elements. So if you imagine that we are made out of material that has belched out of a supernova, and that is continuing. So 4.5 billion years ago, the sun formed out of a similar nebula, at that time sprinkled with heavy elements, and that's continuing. And now we are sampling part of the Milky Way as it is today. So we have 3 nice data points from the Big Bang, the sun's formation, to what is our environment, and then modelers can go on and trace how material has evolved over time in the cosmos. I found that fascinating.
Seth?
Yeah, well, I think humanity has been asking, these fundamental questions since the beginning, trying to put ourselves into this context, and the cosmos has provided this opportunity to do that. And these new discoveries are going to help us address how unique or how special is our heliosphere? Are other configurations similar or different? How do they interact with the planets and around those stars and that sort of thing? And another note that I think is really neat in this attempt to put ourselves in this cosmic context is, despite how close these things are, these closest interstellar clouds and the heliosphere, it's really particularly difficult to study them. And it's a real achievement to measure these interstellar clouds, to measure the heliosphere in this sort of detail, when we're used to thinking that the farther away something is, the harder it is. And that's true to some extent, but these are really difficult measurements, and so it's really exciting to see these results today.
Thank you all. And with that, we'll close out. And again, you've heard the anatomy of our galactic neighborhood. And again, you can find all this information on the internet at www.nasa.gov/IBEX, or again via Twitter, Facebook, YouTube, and other social media sites. Thanks for joining us. Science never sleeps.